This week's lectures are dealing with the basic contrast mechanisms of MRI. And so I want to first, however, start out with a very important message that is dear to me. And this is, we are dealing here with one physical phenomenon, and that is magnetic resonance. We're dealing with one instrument, that is one magnet. But what we are getting out of this modality, out of this biophysical mechanism, is many different contrasts. So we have many different contrast mechanisms. So I want to first start out with some examples. This is a so-called proton density weighted image. So we have a cut through the head here. This is from the brain. And if it's proton density, then essentially what has been imaged here is the equilibrium magnetization. So that reflects the density of the protons in the MRI. Then here's an example of a T1 weighted image. Again, a similar cut from the subject. It's a transversal cut, T1 weighted. And here is a T2 weighted image. So these are some very basic contrasts: proton density, T1 weighted, and T2 weighted. And you can see that just by changing some experimental parameters, one can substantially change the appearance of the image. So here, what is interesting to note here is the cerebrospinal fluid. The ventricles, they are filled with cerebrospinal fluid. Here they are the more intense than the others because they have a bit more water. In the T1 weighted image, they're dark because they have a long T1. And in the T2 weighted image, they are bright because they have a long T2. Here's an example which is more pathological. So this is clearly not a normal part of the brain. This is T1 weighted, and here it's T2 weighted. Now what is this space here? It's dark on the T1 weighted, like the cerebrospinal fluid. It's bright on the T2 weighted, like cerebrospinal fluid. So this is a cavity where tissue has been eliminated. In fact, it is a large cyst. It's just cerebrospinal fluid, probably a resected tumor or some complication early in life. Now here's another example. It's a bit more elaborate that I want to illustrate here, and this is imaging multiple sclerosis. So we're looking at the plaques. So we're looking here first at the T2 weighted image on the left, and we see that cerebrospinal fluid is bright. It's here in the ventricles, and it's also in the sulci. And if one looks very carefully among all these bright signals, one sees some signals here that are somewhere where they shouldn't be. But all this bright signal is difficult to detect. So then the approach that is often used in multiple sclerosis is to use the so-called fluid attenuated inversion recovery approach, or FLAIR, that's the acronym for that. And this is a combination of T1 and T2 weighted. First, what is done with an inversion pulse and an inversion time, Ti, that is such that the signal from the CSF, the longitudinal magnetization from the CSF is zeroed. At that point, when the longitudinal magnetization in the cerebrospinal fluid is zero, the signal is read out and then detected with a long echo time, so it is T2 weighted. What then happens is that these lesions here in the brain tissue, the signal changes appreciably compared to the brain tissue, and there's substantially more contrast to noise ratio. Here the signal to noise ratio is substantially better, but here the contrast to noise ratio that distinguishes these demyelinating lesions from the normal appearing tissues around them is much easier detectable. And finally, we have the T1 weighted image. On the T1 weighted image, because demyelinating lesions are a destruction of tissue, so there's less tissue, less membranes, less proteins around. T1 and T2 are getting longer. T1 is longer. They appear as dark, and they are, again, not as visible as they are here on the middle image. So we have here just the examples, T1, T2, and proton density, that give us already three basic contrasts in MRI. Another contrast I want to discuss this week is T2 star weighted. We're actually going to discuss this contrast first. And with T2 star weighting, what is often done is venography. And the goal here is to use experimental conditions that at which point the magnetization that's in the venous blood has decayed. So venous blood, the signal from venous blood, is darker than normal tissue. So it's a reduction in magnetization in blood. What is a venogram? What does it look like? Here is from the brain. So this is a two-star weighted image, and all these black stripes here that are in here, they're in fact normal manifestation of venous blood that has a short T2 star. It is deoxygenated, and we'll see shortly. We'll discuss this shortly. In research, there has been functional MRI has been coming along. It's based on blood oxygen level dependent functional MRI, or bold fMRI. And what I want to highlight here is an example of the very first images, or some of the very first images that Seiji Ogawa at Bell Labs obtained at the time in the late 1980s from the rat brain. So this is a rat brain under normal conditions. This is what such a T2 star weighted image looks like. And on one day he noticed that in one of the animals, which was having trouble breathing, he obtained an image that looked like this. There were the venous structures that were dark appearing, and general the sensitivity of the signal had decreased. And he had the enormous insight to realize that from neuroscience, we knew that there is an increase in cerebral blood flow much more than oxygen extraction. So this would lead to a change in deoxygenation in the blood vessels, and he proposed at the time that this is possible to exploit in normal brain activation studies to see the activity of the brain. And hence, in the early 90s, the functional MRI was born. Nowadays, the data sets used for fMRI, for brain activation studies, depict data sets like this. So we have the anatomical image. Here are the eyeballs, retrobulbar fat. This is axial cuts. This is a coronal cut. These are sagittal cuts. And overlaid on the anatomical images are the area of the brain that have been activated in response to an external stimulus. That stimulus can be finger tapping, it can be looking at an image, it can be listening to a sound, it can be a mental task, and so forth. Now I want to give here another view on spatial encoding with MRI. Last week we have introduced two-dimensional spatial encoding with MRI, and I'm sure you have found it not the easiest topic to understand. So I want to give it here another try and give you another argument to rationalize how we reconstruct images with MRI. So let's start with the basic experiment. We need to have an RF pulse to flip the magnetization into transverse plane, so we have something that precesses that we can detect. This is done typically with a slice select gradient, so we're selecting a slice like this in the brain, and then we have the frequency encode gradient that is switched. The first part of the experiment is excitation, so and then we have frequency encoding, so two phases of the experiment. We observe here the echo time at this time point, we observe the echo at this time point, and this is defined by the echo time. We have seen that we need this negative gradient, refocusing gradient to have maximal sensitivity to minimize the effects of dephasing under the slice-like gradient. Here's the frequency encoding dephaser, the rephaser, and when these two areas are the same, we have echo. So now I'll introduce a time and I'll call it T2. You'll see shortly why I call it T2 and not just simply T2. So as we record the signal with the scanner, we'll call the time during which this happens T2. And now we're going to look at the signal as a function of T2 starting at this time point. So this is time 0 here. This is equal to the transverse magnetization as a function of position x. We have the gradient here, we'll assume along x. So gradient will assume the frequency code is along x. So magnetization starting here, they're all aligned, they're collinear. And then we have the different precessional frequency based on their position along x. So it's gamma gx times T2 is the phase as it evolves. And of course, the entire signal we see is the summation of all the signals along x. So now the link between the signal as a function of t2, the time domain signal, and the magnetization as a function of position, the link between the two is given by the Fourier transformation. And now we take a standard Fourier pair, time and frequency. So the Fourier transform of a signal in time gives you gives you a function as a function of frequency. That's a standard Fourier pair time frequency. So if we have t2 is our time variable, then omega 2 is we'll call omega 2 the corresponding Fourier pair variable. Now omega 2 is gamma gx times x. That is linked to the position because the gradient is fixed, the gamma is fixed, so this is omega 2 is linearly related to the position. So the magnetization as a function of this frequency is equal to the magnetization as a function of position. Okay, so actually, if we look at a two-dimensional object at a given position in x, all the magnetizations that have the same coordinate along x for this gradient along y, they'll have the same precessional frequency, so we cannot distinguish them. They'll just appear as a stronger signal. And this is reflected that we have to sum along y, all the magnetizations along y for a given position x. That's our magnetization along x. And so it turns out that after Fourier transform of our echo here, of this signal, we're getting m of x, and m of x is the radon transform of the magnetization along the direction x. Now, what we can do is here, this is for a particular direction x, but I have not defined what x is, so I can choose any coordinate system and have x different. And so we can actually change the orientation of this projection, the magnetization of x, by now changing the orientation of the gradient, because the direction of this radon transform is entirely defined by the gradient orientation. So if I now choose a gradient, and remember we have introduced gradient as vector, as a linear combination of with two components, basically with a constant amplitude, but I will rotate it by an angle phi. What this amounts to is that we are recording the projection, the echo, along an orientation that is rotated with respect to x by the angle phi. You can verify that. If phi is 0, then we have a gradient along x. If phi is 90 degrees, then we have a gradient along y. And of course, we can change between the two gradually by changing phi gradually. And so this we can repeat. We can repeat different projections. We'll collect, after Fourier transformation, the radon transforms of our magnetization. We'll do this in many steps, just like with CT. We'll have to take into account that we have to, every time to measure a new radon transform, we'll have to do a new excitation. So this will be done every TR seconds based on the repetition time. This leads to a sinogram. We can, in principle, we can reconstruct then the image with projection reconstruction, or we can make the link to Fourier transformation with the central slice theorem. So if this helps you to understand why MR scans take some time, we are going to have to collect the different projections, the different angles. We can do that just as it has been done in the X-ray techniques, and then reconstruct the image using those techniques is definitely a possibility. So this could convince you that it indeed, A, it is possible to reconstruct an image, and B, why collecting the data of an image does take a considerable time, because if we want to have a 256 by 256 matrix, that means we have to collect 256 angles phi, and for this we have to wait 256 TR periods. TR is linked to T1, so it is typically on the order of the T1 relaxation time, and therefore that explains why it takes typically a couple of minutes to obtain an MRI image. Okay, so if this helps you, but now I'm going to try to look at the phase and cogradient, because the MRI reconstruction and data acquisition is rarely done using the radon transform approach. There are some applications, but they are the vast majority. The major application, the major way of obtaining the image is done by two-dimensional encoding using the phase encode gradient. Now what I want to make here the argument is that phase encoding is essentially just frequency encoding in a second time dimension. So we'll just put in here a phase encode gradient. We're looking here at this time period. It's the third dimension. And now we'll look at here at the y gradient. We've had last week, we have talked about the phase encode gradient having a certain amplitude and a certain duration tau. And if we have now an nth step, then the amplitude of the gradient is n times delta gamma y. That's the gradient strength times y times gamma times the duration. That gives us the phase twist induced by this gradient. So for the nth phase encode state, the magnetization, transverse magnetization, after this phase encode gradient, so right here, is given by the magnetization before, so that's the transverse magnetization here, times this phase term here. And what we have done is we've argued that if we now step through these amplitudes with a decrement or an increment of delta gy, and we do this several times, that this essentially allows us to encode the second spatial dimension. The argument there was that I made, it was graphical to say, well, in the end, the computer cannot distinguish whether we have collected one dimension immediately and the other one step by step, or if we do it in reverse, and therefore these two things are equivalent. Now, what I want to argue here is that we can actually look, if we look here at the gradient times time term, the n delta gy tau, I can rewrite this and I'll say, well, n times delta gy tau, I'll express this as a constant gradient times n times delta tau. So now I have a constant gradient along y, and I have this term n delta tau. What does this mean? So for the nth gradient step, we'll start out with the first gradient step. We'll have an amplitude gy. This is the gradient along y, and we'll have a duration of delta tau. If we do now the second step, then we have a duration of 2 delta tau, and 3 delta tau, 4 delta tau, and so on. 5 delta tau here. So it's up to n delta tau. And now we rewrite the magnetization. The effect of this gradient is again, gradient times time gives you the phase effect. So gradient times time, n delta tau, times y times gamma is the phase term. We're just using this identity here. So we're getting the magnetization now expressed in this form, the evolution of the magnetization under the gradient. And now I can say, well, n delta tau, that's just nothing but a time dimension, which I call t1, that has been discretely sampled at intervals delta tau. So in the end effect, what we are now getting is a signal that depends on two time dimensions. T2 is the time as we record it. T1 has been defined as the time step by step as we increase the gradient duration for this example, but we have seen that this is equivalent to increasing the gradient amplitude step by step. So if we consider the signal is now a two-dimensional time signal, there are of course not two-dimensional times as such, but it's a second virtual time dimension. We can do the frequency, the Fourier transformation, two-dimensional Fourier transformation. We got two time variables, and this gives us from the signal of T1 and T2 gives us a magnetization as a function of omega 1 and omega 2, and therefore a magnetization as a function of gamma y and x, because omega 1 is linked to the position in y here, and omega 2 is linked to the position in x, that's here. So we have a two-dimensional time signal. We can view it as that way. It's not standard-wise done in the MRI, but if it helps you, this is another way to look at it. Two-dimensional Fourier transform gives us two frequencies, a two-dimensional object, and these frequencies through the Larmor equation are linked to position with the gradient condition. Okay, so much to rehash the spatial encoding with MRI, the phase encoding, and I hope this helps you with this relatively difficult topic on understanding how we generate 2D images. Okay, so last week we introduced the gradient echo sequence. This is the basic experiment with which one generates images. We've introduced how the spatial information is encoded. So now the question that I want to go after is, what is the contrast in gradient echo imaging? And here we will introduce T2 star weighting. So we have the RF pulse, which is at an alpha degree. We need this pulse to generate transverse magnetization. It is done with slice selection. So we're selecting a slice here, and the areas of these two gradients are equal but opposite. This is refocusing, so we have maximum signal. Then we have the frequency encode gradient with dephasing and rephasing, and this area here then defines the rephasing. And we have the phase encode gradient. This gives us the signal that is ultimately recorded. We'll set this time here to 0, and here the time is defined by the frequency encode gradient. This is the echo time TE. So this is our basic imaging sequence. This is repeated n times to generate the image. Now what we want to look at is one effect that produces T2 star weighting, and that is to look at the effect of static field imperfection, which we haven't dealt with yet. So far, when I've introduced to you the relaxation times, and so far we have dealt with that the B0, aside from the gradient that we introduce in the scanner, the B0 is perfectly homogeneous in space. And this is unfortunately not true. In very general terms, we can write the static magnetic field, the B around which the magnetization precesses, as the B0. We have the gradient term. Now this can be time variant, as we can see here, times the position, plus a term delta B of R. This delta B of R is nothing but the first order approximation of the Taylor series expansion of the magnetic field, if you will. So it is the derivative of the z component of the magnetic field with respect to position times the position scalar product. This is a vector, this is a vector, it's a scalar product. So this produces a change in magnetic field that is spatially dependent. It is static, it's not time variant, and we can assume that we have an image voxel, and in that image voxel we don't have a perfect B0. So we have a distribution of magnetic fields in that voxel of our image. So what happens now? This basically means that if we have a dBz to d along z, then basically what we've drawn here, the gradient as 0, it's actually not truly at 0. There is a little offset here that is caused by this term dBz to z times z. Same for x, so this is dBz derived by x times x, and the same for y, the y direction. We're here just thinking about a particular voxel. So now our magnetization at time TE, the signal here, our echo at this time, is given by the magnetization just after the pulse. We'll assume we have perfect refocusing of the slice selection. Then we have e to the minus I gamma from 0 to TE, the effect of the gradient. Actually, you can include the slice here as well. This will be nullified, but we have the effect of the gradient, and we've seen that the phase term is proportional to the time integral of the gradient over gradient of t times r. And then we have the term here from the static field, e to the minus I gamma, again integrated from 0 to TE, delta B of r dt. That's our deviation. That's producing also a phase. So we are not perfectly at the Larmor frequency now for at a given position r, and then we have the T2 effect here. So what this means now is that if we look at this term, this is an area, this is the area under the gradient, the effect of the phase. This is also an area under a gradient, because we can write this as a gradient, just like here, but now it's a static gradient that doesn't vary in time, it's constant. And so essentially we have now the phase effect of this static imperfection is and in addition to the effect of the gradient. And now we're going to be concerned with the effect of this gradient. We can write this now empirically. What one typically writes, that this is equals given to actually, this is the integral directly evaluated, so delta B does not change with time, so delta B times TE, that's the phase effect. And so now what we are going to do to understand what is the effect of this area here, the blue area in the three directions, we're going to use the feature that I introduced last week, and that is that a gradient applied simultaneously or sequentially before the echo has the same effect on the echo phase. So what we're going to use now here is that the gamma delta B times TE, I can write this as gamma times n times delta B times TE over n. You see, I multiplied by n and divided by n. What does this mean here is now I can pretend like I'm implying a n times bigger static field homogeneity for an n times smaller time period. The effect of on the phase will be the same. You can verify this term is in here. The n cancels out, so mathematically it has no influence on the image phase, but we can easier visualize this. So let's look at the phase encode gradient, which now here appears in green. I will do this now. I will shorten the duration of this inhomogeneity. I'll pretend that it's only applied for a short period of time, and I'll increase the amplitude by the same amount, so it is now n times bigger. The area stays the same. And then I will just say, well, I can, again, with the properties I introduced last week, we can say that this gradient is applied for a short time just before the phase encode gradient. So what does this mean? So if we have a voxel where there is a gradient along y in that voxel, it has an effect on the magnetization phase as if we had for a short time turned on an additional gradient that corresponds to the dB z derived by dy, the gradient y, static gradient times, as if we had turned on a little gradient here beforehand. We can do the same, and I'll change the color here for the readout. So we have the area in orange here. We'll shorten it, increase the amplitude, and now we'll move it somewhere else. So what do we see here now? For a perfectly balanced imaging sequence, we see the area here is the same. So the area, the echo will be here. Now the effect of this inhomogeneity is to have a changing the area here. This is of course a huge exaggeration here, these effects. But the effect here of the inhomogeneity is to introduce additional dephasing, and this will change a little bit the position of the echo. So not much to worry about. However, we have the z gradient. We'll do the same thing here. So we'll shorten the duration. We'll just mimic again the effect of the long time period. We'll pretend that the effect of the static gradient here is being described by something that's much shorter but has n times larger amplitude. So I'll do this. I'll shorten it, increase the amplitude, and I'll put it somewhere else. What is happening here is now we have said we need to have the area of this gradient equals to the area of this gradient. Now the static inhomogeneity is changing the area of this gradient because it's in this direction. And so now we no longer have perfect refocusing of the magnetization along z. So we no longer have maximum signal. This gradient reduces our amplitude. This gradient in the read direction shifts the echo time. Usually it's not perceptible. And in phase encode direction, this additional gradient here will introduce a phase encode, an additional dephasing that can be substantial. So we have, as a result, we have a reduction in signal amplitude. And this we can verify. We'll take this expression here that we've had, and we'll now sum the magnetization over one voxel. So the e to the minus te over t2 is constant. We'll take it out. It's a three-dimensional integral over the voxel times this phase term over the echo time. That's the effect of the phase of this term here. We'll assume that all these gradients have cancelled because we're exactly measuring here. So now this term here produces a dephasing integrated over the voxel. So we have all sorts of different precessional frequencies in our voxel. This will create a dephasing that increases with TE and therefore a reduction in signal. Now what one does here is very empirical. We'll just say, well, the signal actually is still decaying exponentially, but now with a time constant T2 star. We'll call this time constant T2 star. So, and empirically there's a relationship between T2 star and T2. So 1 over T2 star is equals to 1 over T2 plus gamma delta B. Delta B is always considered to be a positive term, gamma is positive, so this is the right side is bigger. If the right side is bigger than T2 star is smaller than T2, or T2 is longer than T2 star. So delta B is here really an empirical parameter, a fudge parameter that just describes the degree of inhomogeneities, but it is a way to quantify the inhomogeneities that are present in the voxel. So to summarize, the effect of static inhomogeneities, imperfections in the static magnetic field, creates a faster decay of the signal that is faster than pure T2, and also an opportunity for additional contrast, which we'll see in the next section.